Yeah, so this R simply means real. So the entries of this matrix are real numbers. So O2R, yesterday we discussed O2R and the SO2R. So O2R was the set of all orthogonal 2 by 2 by 2 real because that's real there. Orthogonal matrices. And here we have, so this of course means that if M belongs to O2R, then it satisfies this condition, M transpose M equal to identity. That was the definition of orthogonal matrices. And SO2R is a subset of this O2R in the sense that the matrices here must also be orthogonal, but we have an extra condition, and that is determinant of M equal to 1. So SO2R satisfies both of these conditions together, whereas O2R just satisfies that. Okay, and we also saw last time that this condition is basically since notice that these are conditions, right? So you want to compute how many parameters are there, how many continuous parameters are there in these matrices which satisfy this condition. Well, to begin with, it's a 2 by 2 matrices, so there are 4 parameters, right? They are real, so 4 real parameters are there. But then here I have a condition, 3 conditions, 3 independent conditions, because this left-hand side is symmetric, right? So a symmetric matrix, so there are 3 real conditions. So out of the 4 original variables, we have 3 conditions. So there must be only 1 parameter. So this tells you that there is just 1 parameter, 1 continuous parameter. Determinant of n equal to 1 does not reduce the number of parameters. That is because if anything satisfies this equation, taking the determinant of both sides, you find determinant of M transpose M equal to 1, right? Determinant of 1 is, determinant of identity matrix is 1. And now this guy is the same as determinant of M transpose times determinant of M. But this determinant of a transpose is the same as determinant of the original matrix. So this is determinant of M squared. So that means determinant of M can only be plus or minus 1. So it's not like there's no continuous parameter there. They're discrete. Okay. So this does not give you any extra condition. It gives you a condition, of course, but it's not going to reduce the number of parameters, right? So the number of parameters is still 1. And indeed, we found that the matrix which satisfies this condition is this one. Okay, this is an element of SO2R because determinant is 1, and indeed you see that there's only 1 parameter here. Okay. Now before, so I wanted to, and we also saw one important point, that if you think of this as, these are 2 by 2 matrices. See, whenever you see matrices, you can always think of it as a linear transformation in some vector space. So this is a 2 by 2 matrix, so you can think of this as a transformation on a 2-dimensional vector space. So the way it acts is you have this matrix, and you just consider 2-dimensional space, 2-dimensional vector space xy. So by multiplication, so we are saying that xy goes to, under such a transformation, goes to this. So this is a transformation. So that's why matrices are very useful, because they can be always thought of as some linear transformation, right? Symmetries in general may not be linear, right? But when you realize some group as a matrix, some group elements as matrices, a set of matrices, then they are always, you can think of it as a linear transformation. So that's right. So we saw this cosine theta minus sine theta, cos theta, and this was nothing else but just a rotation in the 2-dimensional. Okay. So I have a 2-dimensional plane here, x, y axis. So take some vector and you rotate by an angle theta. That's what this matrix does. So it's a rotation. Okay. That is for the SO2. If you have also, if you consider O2R, there is also you allow negative determinant, right? So O2R will have an element, for example, -1, 1. Okay. This is not, you cannot get it from here. That is because the determinant of this is -1, whereas this determinant is always 1. But this also we understand geometrically what it does. If you apply that on x, y, it is just a parity, just a reflection in just one direction. Right? So those are the symmetries that we see. Now before I go to the, so that's what I wanted to say. So the important point of this was a rotation, and you can actually define this, SO2R as saying that it leaves, I mean, so when you make a rotation, what is invariant? The length is invariant, right? So I have a vector here. This will just rotate the vector, but the length will not change. Okay? So what we are saying is that x squared plus y squared, so under SO2R, and actually both O2R, both of these guys leave x squared plus y squared, the length, total length square, invariant. This doesn't change. So one way to define this O2R and SO2R is a group of linear transformations which leaves this length square invariant. Now, what's the difference between O2R and SO2R? You see, I mean, if I consider now a volume form, meaning, say, if I consider an integral dx dy of some function of xy. Okay. Now, if you make a transformation of coordinates, right? So let's say this xy, so this is xy goes to x prime y prime, which is equal to that. So you can make a coordinate transformation. Instead of integrating over x and y, you can integrate over x prime and y prime, right? But then, in general, when you make such a coordinate transformation, there will be Jacobian, right? And that Jacobian, if you have determinant equal to +1, that Jacobian is +1. Okay. Whereas if you have determinant -1, you see, if you apply this guy, what will happen? X prime will be equal to -x, and y prime equal to y. So dx dy will become minus dx prime dy prime. So there will be a minus sign. Right? So the SO2R are the ones which which keep the volume form invariant. Right? Not only it keeps the length square invariant, but also the volume form invariant. Another way to say, the orientation doesn't change. The orientation doesn't change. That's the equivalent statement. The orientation doesn't change. Whereas by reflection, of course, you change orientation, right? Mm-hmm. That is the difference between the two things. Okay, so x squared plus y squared, right? This is, of course, a Euclidean length square, Euclidean length square, right? You have seen the relativistic quantum mechanics, I mean this relativistic course, that you have a Minkowski signature where the length square is x squared minus y squared. Okay. And one can again ask the question, what is the group which leaves that length square invariant? But before going over there, let me go to another, before I discuss the minus case, okay? Let me consider another group, I mean seemingly another group, which is exactly the same as SO2R, okay? So let's do that here now. You see, just like we discussed, we described the O2, or more generally you can talk about ON, right? ON would just mean replace this 2 by n. N cross n real matrices will satisfy this condition. Okay. Same way, you can talk about complex spaces. Okay. For the simplest one is simply one complex coordinate set. And of course, it's complex conjugate Z bar. So one complex is the equivalent to 2 real, no? Is a plane. So Z. And I want to ask, or more generally, I can take n of them, Z1, Z2, up to Zn. And we consider the most general transformation, okay, on this space, this complex space. So this goes to some, let's call it some matrix again, M. So linear transformation, Zn. In such a way that this length, Z1, Z1 bar, plus Z2, Z2 bar, etc., plus all the way up to Zn, Zn bar. This is invariant. This is invariant. So the complex spaces, that's the way you define the metric. The complex number times its complex conjugate, right? That is the length square. Right? So this will be the analog generalization of that. So you want to consider all the transformations which leave this length square invariant. But notice, I mean, of course, each complex number is like two real numbers. Okay, so this is really 2n real numbers. Okay, so you could say, okay, 2n. So in other words, if I write Z1, Zi as Zj as Xj plus Iyj, right? I can write each of these complex numbers as that. Then Zj bar is Xj minus Iyj. Okay. And Zj bar is simply Xj square plus Yj square. Correct. So this length square is nothing else but the sum over all the 2n real coordinate squares, right? Sum of the squares of all the 2n real coordinates. So it's really 2n dimensional Euclidean length square. And then the most general group of transformation which leaves that length square invariant will be O2n, right? O2n. That is what we. But here we are not considering the most general transformations. You see, we are saying that we are not going to allow to mix a complex coordinate with its complex conjugate. You see what I'm saying? I mean, the most general transformation, if I write it like, if I write x1, y1, x2, y2, all the way up to xn, yn. So this is 2n real dimension. If I consider now 2n by 2n orthogonal matrix, it is going to start mixing up all of these things in a random way. Not completely random, this is orthogonal, right? But it will not preserve, I mean, it can mix, for example, some z's with some z bars, right? But here, when I'm doing such a transformation, I'm saying that no, I'm not going to allow such mixing. I'm going to make transformation so that z's go to z's only, not z bar. Okay? So it is clear from this description that this group will be a subgroup of O2n, right? That is clear. Right? It's a subgroup, but it's a very important subgroup. I mean, you know, because I mean, you'll see that in particle physics, this is the kinds of groups that appear all the time. So, what would be then the equation? What would be the conditions on this matrix? Once again, we can write. So let me just write this capital Z. Capital Z is this column vector. So this I call capital Z. Capital Z is that. Then I can define this length square as Z dagger times Z. Right? So this was this vector. So you have n rows, and 1 column. Right? Z dagger will be, so you remember dagger is what? Transpose and complex conjugation. Right? So the Z dagger will be 1 cross n. This is n cross 1. So this product will be a 1 cross 1 matrix. And indeed you can see what is Z dagger. I mean, Z we said is Z1, Z2 up to Zn. Z dagger will be, just take the transpose and complex conjugate. It will be Z1 bar, Z2 bar, all the way up to Zn bar. And now take the product of these two, and you will find exactly that. Z1, Z1. So what we want in this matrix notation, that this must be invariant. Okay. Now let's take this. So we said, okay, suppose matrix M satisfies this condition. Okay. Then what is, so if Z goes to Z, Z goes to M Z, then Z dagger will go to, just take the transpose complex conjugation of this, it will be Z dagger, M dagger. Okay. And now you see what will happen. So this object, the length square, will go over to Z dagger, M dagger, M Z. So if length square should, if our requirement is the length square doesn't change, then that means that this M dagger M must be equal to identity. Okay? So that's the definition. So that means this matrices M, I mean those matrices which satisfy this condition, they are called unitary matrices. Okay? Unitary matrices are the ones such that the inverse of a matrix is the dagger of the same matrix. Okay? So that's the unitary. So this is a definition of unitary matrices. Okay. Just like that original, for the orthogonal we had this condition, M transpose M equal to 1. In that case we call such matrices orthogonal matrices. Here then in the complex case, if M dagger M is identity, so this is identity, okay, then such matrices are called unitary matrices. Here's a definition, terminology. Okay. So, okay, that's one thing. So this is usually denoted by UN. UN. UN is the set of all n cross n unitary matrices. Now we have to of course check whether this is a group. It's a set at the moment. It's a set. Huh? It's just a set. Sorry.
It's not the matrices M. It's the matrices M dagger with M. But we have only one unitary matrices.
No. Just like in the orthogonal case, there are many. I mean, this is the definition. This is the condition satisfied with the matrix. Now you can ask the question: how many parameters are there? No, that will come to. Huh? But it's a set of all such matrices. Just like here, I mean, there are for O2R. You see, there were all this. The one parameter family of matrices, right? Parameterized by theta. Same way here also there will be, depending on the value n, depending on what is the n, you will have many parameters. So this is a set of all n cross n unitary matrices. Then first of all we need to check whether it's a group. So to check that, let's look at, if I suppose U1, suppose M1 and M2 are in UN, then we want to check. So we want to check now that this forms a group under the usual product rule for the matrices. Because when you say group, you have to also you have to also specify what is the product rule, composition rule. No? So it's what we are saying that is a usual matrix multiplication. So we want to check. So what we want to check is if this is in UN, then M1, M2 in the usual matrix multiplication, this also belongs to UN. This is what we want to check, right? Then this implies that. So let's check that. So what we want to check is if M1, M2 is unitary. In other words, we want to check if dagger of this times this itself is identity or not. So I take the dagger of that, and when you take the dagger again, order changes, right? Just like transposition, order changes. So dagger of this guy is M2 dagger, M1 dagger. Right? And I multiply this, and then use the fact that M1 and M2 are unitary. So M1 dagger times M1 is identity. Right? This becomes identity. Then M2 dagger times M2 is identity. So this is identity. So therefore, this is true. Now, what about the identity? The associativity you don't need to check because matrix multiplication is associative. Okay? Because if you had used some different multiplication rule, then of course you need to check. But these things we know. The matrix multiplication is associative. What about the identity? Identity is just identity matrix, right? And identity matrix, of course, is unitary. Because if suppose in that equation we had M, if you take identity matrix, then dagger of identity matrix is again identity, and that times that is identity again. So identity is surely unitary matrix. So identity exists. And finally, inverse. Okay. Now, so to check if, so as we said, matrix this is just the usual multiplication, matrix multiplication. So inverse will be with respect to the usual matrix multiplication rules, right? But we know for the usual matrices, the inverse will exist provided, I mean, if and only if determinant is not 0, right? So let us check the determinant condition. So we have M dagger M equal to identity. So take determinant on both sides. So here you will get determinant of M dagger times determinant of M, and that side you get 1. Determinant of identity is 1. But determinant of dagger is transpose and complex conjugate. Determinant of a transpose is the same as the determinant of the original matrix. So this is the same as determinant of M complex conjugation, right? So this is the same as this star. Okay, I don't know. Sometimes I'll just use bar. Bar means complex conjugate of that. So this left-hand side is determinant of M modulus square, right? Modulus of determinants square. But in any case, since this is not 0, then the determinant of M cannot be 0. And therefore, inverse exists. Okay? And now all you need to check is M inverse is also unitary, right? So M inverse exists, but in the sense of the usual matrix multiplication. So such a matrix exists, but now we need to check whether this is a unitary, right? So to do that, I just take again the dagger of that. So that is M dagger inverse, right? The M inverse dagger is the same as M dagger inverse, but this is the same as M dagger inverse, but M dagger is identity, so this is equal to 1, identity. So that tells you that M inverse is unitary. So this forms a group, UN forms a group. Yeah? Now, once again, just like the relation between ON and SON, we can impose one more condition. This was the set of all n cross n unitary matrices. But now we can define a subgroup, a smaller set. This is contained in the UN by imposing one more condition. One more condition. Namely, the determinant of M is 1. Notice that we already checked that the fact that it's unitary implies the determinant of M modulus square is 1, right? Unlike in the ON case, there was no complex conjugation, they were all real, right? So you have just determinant of M square was 1. So there was only two possibilities, determinant of M is plus 1 or minus 1. Now, however, determinant of M modulus square is 1. So determinant of M can be a pure face, right? So this implies that determinant of M is some pure phase, which means some e to the power of I, let's say some phi, right? So it is not, see there is one parameter here. No. Okay. So that means when I impose this condition, I am going to set that parameter equal to 0, right? So I am going to reduce one parameter.
So it's additional.
Yeah, it's dimensionally one less. It's this dimension of this will be a one less than the dimension of that. Unlike in the ON case where dimension didn't change. Okay, now let's see what is the dimension of this space, I mean this set, meaning how many parameters are there. The same counting we'll go through. If you look at, so the equations are that. I mean, first let's look at the UN. So you have M dagger M equal to identity. Okay. So question, first of all, UN is an n square entries, which are all complex numbers. Right? UN, these are complex numbers. So to begin with, I have n square complex numbers, or equivalently 2n square real numbers. Right? Because each complex number is like 2 real numbers. Right? Any complex number you can write as x plus iy. Right? So since I have n square complex, that's the same as 2n square real. Parameters are there. Now, how many equations are here, right? You know, if you take the dagger of this guy, left-hand side, this is dagger of that is itself, right? So that means the left-hand side is Hermitian. Okay. So if I look at this, what is a Hermitian? It means I've got some diagonals. Diagonal must be real, Hermitian, and this part, this triangular part, will be the same as this triangular part, I mean transposition, but complex conjugate of them. Okay. So you see how many independent equations we have. We have n diagonals, so you have n real equations there, right? I mean, when you impose this condition, there are n real equations from the diagonal. Plus, if you look at the off-diagonal terms, how many are there? Half n times n minus 1. So you have half n times n minus 1, but that is complex equations. Okay?
So multiplied by 2.
Multiplied by 2. So that's a total number, so real. When I multiply by 2, meaning these are the complex equations, which is equivalent to 2 times that real equations. Right? So those are real equations. So altogether, 2 cancels, you have got n square minus n plus n, so n square equations. N square real equations on 2n square real parameters. So that will fix n square parameters, but remain still leave n square parameters. So therefore, this group will have n square real parameters. And when I go to SUN, as we saw, this determinant condition just gives you 1. Determinant is only a phase. So when I set this equal to 1, I have to just set phi equal to 0. So one of the parameter is set to 0 here, right? So this has n square minus 1 parameters, real parameters. So that's the way the counting goes. Again, as I said, when we go to the infinitesimal generators, this counting will become much easier because these equations are still nonlinear. You might wonder maybe there are some problems because quadratic equations, there can be problems with that, no? So you might wonder, but once you go to the infinitesimal transformations, it's all linear. These constraints are linear, and then you can easily count.
This structure is not disconnected, like all,
no,
right?
Yeah, exactly. Because I mean, the determinant is a continuous. There's a parameter there. In the ON case, determinant was +1 or -1. So there were 2 different sectors.
So to have a totally connected set, we choose determinant 1 part of that and name it as SO. But in that case, we specify an SU, but is it really needed or?
Well, let's see. I mean, we'll see that's a
trick for the determinant, and we set it to a real number, real 1.
Yeah.
But we didn't need.
You didn't need to. But it depends on your physical problem, and we'll see that as we know, in standard model, the groups which appear are SU2 and SU3, right? Both are S, especially. But okay, you may have some other fields. There's also U1. So it's U1 cross SU2 cross SU3. But we will see later that in terms of even mathematically, with the classification of Lie algebras, SUNs are playing a very special role. These are something called simple algebras. Whereas if you take UN is not a simple algebra. Simple in a technical sense. I don't mean it's more complicated. No, it is just that there's a definition in mathematics which is called. There's some algebras are called simple algebras. So SUNs are simple algebras, but UN is not. So even from the mathematical point of view, if you study the algebras, you study SUNs. If you know SUN, then UN is immediate, because UN is, essentially UN is a U1 times SUN. Okay. Because the only thing which you are setting to 0 is this phase, and that phase is the U1. Okay. So up to some global identification, SUN is essentially SUN times U1.
It's like Z2 times SO, so it's like O2.
Yeah, that's what it's like. Yeah. Yeah.
But
But here it's completely connected space. UN is completely connected.
is it n squared or n squared minus 1?
Here it's n squared minus 1, not there.
No, minus n, I mean, because we subtract this quantity from that one, right?
Because so there I have a total number of equations. These were the equations coming from the diagonal.
Okay.
Right? These were the equations coming from the off diagonal.
Ah, I see.
So the total number.
We sum them and then.
Yeah.
I see.
Okay. So in particular, now let's look at just the U1. Sorry. Go ahead.
Date M is e to the I pi, right? But if the group is connected, then it will pass at some point date M equals 0.
M equal to 0?
It's just
No, P equal to.
okay.
Determinant of M. This is a, I mean, its length is always 1, right? Phase. E to the I phi mod square is 1, right? Because complex conjugate e to the I phi is e to the minus I phi. You take the product, it is 1, right? Yeah. This is just a circle. As the phi changes, it's a circle, right? Unit circle. Okay. So let's now look at the U1. Let's look at the U1 and see if U1 is somehow related to O2 or SO2. Because the number of parameters is the same. You have n equal to 1, the number of parameters 1, 1 square is 1, and O2 or SO2 had also 1 parameter, right? Now that, certainly it cannot be O2. So for the U1, now I'm looking at the U1, so it is simply e to the I phi, nothing else. It's just a 1 by 1 matrix, which is unitary, so it's just e to the I phi. This is connected, so it cannot be O2, right? But it might be SO2. So that's the question. Well, U1 is a 1 by 1 matrix, so I can think of it as acting on one complex variable, right? So I have just one complex variable, Z1. So Z goes to, under this action, it goes to e to the I phi times Z. Right? But now if I write Z as afterwards any complex number, I can write it as that. Right? 2 real numbers. So this will go to some x prime plus I y prime. Right? Now what is this? Well, this guy is nothing else. I just multiply this. So e to the I phi itself is cosine phi plus I sine phi. Correct? You're familiar with that, right? E to the I phi. So right, x is z is x plus I y. Just multiply this out. So what will happen? Z is, so let me write it explicitly. Sine phi x plus I y. But then let's again separate into real and imaginary parts. So the real part is cosine phi times x, and there's an I square, which is minus. So you get here minus sine phi times y. And the imaginary part is cos phi y plus sine phi x. But this is exactly the SO2 transformation we saw, right? I mean, you see, so this is what we planned. We said x prime y prime, xy goes to x prime y prime, which is cos phi minus sine phi, cos phi acting on xy. And so you see x prime is cos phi times x minus sine phi times y, which is exactly what it is, this one here. The real part is what I'm calling x prime. Okay. And the imaginary part is simply sine phi x plus cos phi y, which is that. Right? So actually U1 is in fact identical to SO2. Right? If you think of the complex variable z as some x plus iy, That's exactly the SO2R transformations on X and Y. So this is just yeah. Okay, but that's just an accident here. It doesn't happen for higher values of n. Okay, this doesn't happen. Well, yeah, okay, yeah, with some exceptions. There are some exceptions there, but in fact, we'll study soon, maybe on Thursday, that that there's another. If you take SU2, not U2, but SU2, that will be the same as, more or less the same as SO3. Okay, not exactly equal, but very close to being equal.
When we say the same, if there is a map which is 1-to-1 onto between the two sets, there is a that's what we call the same.
You mean? Yeah, correct.
Yeah,
I mean,
like
in this case, it is 1-to-1. In this particular example, U1 is exactly isomorphic to SO2, not O2 because this is connected.
Yeah.
But we'll see that on Friday probably, or Thursday probably, that if you take SU2, then this is almost the same as SO3, but not quite. It's a 2-to-1 now. 2 points here will be mapped to 1 point there. But if you're looking at just infinitesimal transformations, they are the same.
Is it related to spinors are?
Sorry?
Is it related to the fact that the spinors are somewhat kind of have a vector?
Yeah, in fact, it is. I mean, actually, yeah, indeed. If you take the SO3, if you take the spinor version of SO3, then you'll get SU2. Yeah, exactly. In this particular
so SU2 is the spinor representation of the rotation.
Or let's say it's a spin group. It's called not a yeah, you can not representation exactly, but there is a double cover of this group, which is called spin 3. In fact, for all the orthogonal groups, you have to go to the spin version of that is a cover of this group. And in this particular case, when you go to the cover of this group, which includes the which can deal with also spinor, because SO3 cannot act on the spinor, because when you rotate, the spinor doesn't come back to itself; it comes back with a minus sign. No? So you have to appropriately take a double cover of the original group, which is called the spin group. That spin group, spin 3, is called spin n. So spin 3 happens to be the same as SU2. Okay. Yeah, I mean, at some point, yeah, okay. So we'll discuss that. Since you mentioned the spinor, maybe towards the end of this course, if I get some time, I will try to discuss the spinor representations for orthogonal groups, SONs in general, and try to construct for you the actual spinor representations there. All right. So this is fine. Now let's go back to. The.
So we don't call SU2 the spinor representation of SO3.
It's a spin group, a spin 3. It's a group itself. This is a group, right? I mean, SU2 is a group.
Yeah.
So you can say that the spin group, spin 3 group, is the same as SU2 group. Yeah. Yeah, actually you can also think in terms of
I
representation.
think Sokolov
Yeah.
in the book Quantum Field Theory, Quantum Electrodynamics is calling SU2 spinor representation.
Yeah, you can also call that in this case, yes. In this case. In general, it will not be. I mean, spin group, the representation, spinor representations, I mean, if you take, the dimensional spinor representation grows very rapidly. It grows like n square. Okay. So, not n square, even 2 to the n, sorry, 2 to the n. Okay. So, the spinor representation of, let's say, of SO2n goes like n squared. So, it grows very rapidly. So, in this particular case, this was SO2n plus 1, and also for SO2n plus 1. The spinor representation of SO2n plus 1 is the same as the spinor representation of SO2n. I mean, dimensionality of it. No? So you can see for n equal to 1, you have equal to 1. I think there should be maybe 2n square, I'm not sure. But it grows like n square. It's quadratic, not. So you'll find that it is n two-dimensional representation. But suppose I go SO5, it will be 4-dimensional representation, or SO 10, it will be 32-dimensional representations, and so on. So it grows very rapidly. Okay. And now, so let's now just briefly discuss the case of the. So O2R, SO2 or O2 was preserving this length square, x square plus y square was invariant, right? Okay. But what if I, instead of considering this a Euclidean space, so this is Euclidean distance. Okay. What if we go to the Minkowski case? Minkowski. Well, in Minkowski case, say one of them is time and other is a space, then time, there's a relative minus sign, right? So you can, so the length square will be x square minus y square. And I want to consider the group of all transformations which preserves this length. Now again, I can use a matrix notation, x, y, then this length is the same as x, y, but with not identity matrix here, either 1 and minus 1. Right? I can write this object as that. Let's just give it a name called eta. I don't know if this is the notation you were using in the relativistic quantum mechanics. This is a Minkowski metric. Let's say eta. So then, what our equations are, what we have is, if I call capital X as xy, then this length square is nothing else but x transpose eta x. Okay. That's what it is. X transpose is that, and eta is this metric. I mean this metric times x. This must be invariant. That's what we are saying. Okay. So this must not change. Must not change when I make this transformation. So let's suppose this goes to some matrix n times capital X. So x goes to some matrix n, 2 by 2 matrix n times, and all real, because the x and y are real variables, so we are only allowing real matrices. So this is 2 times 2 real matrix. And then plug that here. So you find that this guy goes to x transpose n transpose eta and x. So if it does not change, then it means that this must be equal to identity. This must be equal to eta, right? Because the original thing was x transpose eta x. So if this does not change, if the length square doesn't change, that means that this guy must be equal to eta. That's the condition. Okay, so we can then see what is the most general expression. And this time you'll see that m is okay. For example, okay. So we can just try to see that. So if m is, let's say, a, b, c, d, then transpose will be a, d, a, c, b, d, and I have this 1, 0, 0, minus 1. Okay. This should be equal to 1, 0, 0, minus 1. That's what we are saying. So just open this up, so you get here a.
Not the identity.
Eh? Not the identity, because I mean, you see, the original thing was x transpose eta x. Mm-hmm. Right? Now we have x transpose eta m transpose eta m x, right? Yeah. So this better be equal to eta to reproduce the original thing, right? And so we have a, b. Okay, so one has to work it out. C d minus d, and then multiply a, c, b, d. So you will find here a square minus c square, a square minus c square, a b minus cd, and ba minus cd. So this is the same, and b square minus d square, okay. And that should be equal to that. Now in the O2 case, it was a cosine thetas and sine thetas, because these signs were plus here, a square plus c square. Okay, I mean O2 case this was 1, and that was also identity. Right? So there was no minus sign here, right? So these are all plus signs here. In that case, you have trigonometric functions. Cos square theta plus sine square theta is 1. But now it's because of the minus sign, these are hyperbolic functions. So cos hyperbolic and sine hyperbolic. So you can choose, so I'll just give you that solution answer. So I can choose this to be cos hyperbolic lambda, sine hyperbolic lambda, and sine hyperbolic lambda, cos hyperbolic lambda. Okay. This is correct. Let's see. So I'm taking a to be cos hyperbolic square, c to be sine hyperbolic square, cos hyperbolic, I mean this satisfies the condition, cos hyperbolic square lambda minus sine hyperbolic square lambda equal to 1. Okay, this is what the hyperbolic trigonometric analog of trigonometric functions. So the sine flip, cos square theta plus sine square theta equal to 1, but when you have hyperbolic quotient signs, it's a minus sign. So, I mean, you can write, if you're not familiar with cos hyperbolic, you can write it in terms of exponential. Cos hyperbolic lambda is e to the lambda plus e to the minus lambda divided by 2. And sine hyperbolic lambda is e to the lambda minus e to the minus lambda divided by 2. So if you plug that in here, so when you take this this square minus that square, only the cross terms will survive, right? And the cross term is 2 here, but divided by 4, so 1/2. And cross term here is 1/2 also. So that adds up because there's a minus sign. It adds up and gives you that. So that's that. And then, so let's see. So this is A, B, and C, and D. I just want to check whether I've put the signs, okay, consistent signs. A square minus C square is okay. B square minus D. B square minus D square is supposed to be minus 1, which is also that, cos square minus sine hyperbolic square. Then AB minus CD. So this minus CD, that's also 0. So this is correct. Okay. So this is the solution. I mean, this is a solution, a class of solution, one parameter family of solutions. And this object, you see, has determinant equal to, determinant of this guy is cos square lambda minus sine square lambda, which is 1. So determinant of this guy is equal to 1. But you can, of course, you also have, you can just consider the parity transformations. It doesn't change. Okay. So there's analog. You can have put a minus sign, multiply this by minus 1, 1, 0, 0, etc., etc. But this is like the continuous part, the continuously connected part. Okay. So that's the main difference here. So the main difference is that compared to the orthogonal group, in the Minkowski case, what you have is the hyperbolic functions. But as a result, you see this group is non-compact because lambda can go all the way up to infinity. Unlike cosine theta, theta is going from 0 to 2 pi because after 2 pi you get back to the original guy. Huh? So the space is compact, but here it's non-compact. Actually, one nice way to visualize, to understand this transformation is the following. You see, when I write something, I can always write, I can go to the, I don't know if you have seen something called light cone coordinates. You're not seen, probably. But you know, I can rewrite this as x plus y times x minus y. Right? I can write this quantity as that. Call this as x plus, just give it a name, x plus, and that is x minus. Then length square is x plus times x minus. Okay. Now I want this to be invariant. How can I make it invariant? I can scale this x plus to some by e to the lambda. Then I have to scale x minus by e to the minus lambda. That's what it is. And indeed, you can see explicitly from there, if I look at that transformation. Let's look at this transformation. So x prime y prime, we are saying, is equal to cos lambda, sine hyperbolic lambda, cos lambda, acting on xy. So just open it up. So this is the same as cos lambda x plus sine hyperbolic lambda y, and here you get sine hyperbolic lambda x plus cos hyperbolic lambda y. And then, so x prime is that, and y prime is this, right? X prime is this, y prime is that. But now let's look at what is x prime plus y prime, and x prime minus y prime, right? I want to look at these combinations, x plus y and x minus y. Okay. So let's look at this plus that and that minus. So from this thing, you see that x prime plus or minus y prime will be equal to this plus or minus that. Right? So let's collect the x and y. X will be, the coefficient of x will be cos lambda plus or minus sine lambda, sine hyperbolic lambda. And for this, you'll have y, coefficient of y will be sine lambda plus minus cos lambda. Okay, that's what. But this object, you see, you can combine because the coefficients are the same. If I take out a plus minus here, okay, so I make it plus minus, then I can make this plus and that becomes plus minus. Okay, then this combination is the same. Okay, so you find this is nothing else but x plus minus y times cos lambda plus minus sine hyperbolic lambda. So conclusion is the x plus prime. So from this we can read out where x plus is x plus y, x minus is x minus y. So we see that x plus prime is equal to, I just choose the plus sign, is x plus, and here is plus sign. But then if you just use this equation, cos plus sine hyperbolic, e to the minus lambda cancels, and you just get e to the lambda. Half becomes 1. So this becomes e to the lambda. Okay. And x prime minus is, I just choose the minus sign here. So this guy becomes x minus, because this is minus now. And that becomes cos minus sine. And when you take the difference of these two, this time e to the lambda will cancel, and e to the minus lambda will add up. So this will become e to the minus lambda. Okay. So this is exactly what I said. The transformation which leaves this length invariant is if you scale this by e to the plus lambda, I should scale this by e to the minus lambda. Okay? Doesn't change.
But why is this coordinates are convenient in the case of Minkowski metric, but not in the case of the Euclidean metric?
In Euclidean also, when we see, but you have to put a x plus minus iy. That is going to z and z bar. Right? So in that case, yeah.
Instead of e to the power lambda, we will use complex number.
Exactly. That's why, because when you enter the U1, okay, you see x and y together is like one complex plane. X plus iy equal to z. Yes. And in terms of z, the transformation was simply z goes to z times e to the I theta. Right? Exactly that. Yeah.
We can present in those new coordinate system a new matrix for M, which is diagonal exponentials. So, right?
Yeah, in this
new coordinate system.
In this new coordinate system,
is also a solution for the ABCD matrices.
Yeah, but now you see the metric is different. The metric is off diagonal. right? If I want to write, yeah, let's see what you can exactly. So let's do that. So here, what I'm saying is that, so I have now my coordinates x plus and x minus. Okay. Now I take the transpose of this, so x plus, x minus. But now, what is the metric here, which will reproduce that? It will be 0, 1, 1, 0, right? Or maybe half, it doesn't matter. Yeah? Maybe there's also, yeah, it's okay. So, yeah, I mean, if you wish, you can make it a root 2 here. It doesn't matter to make it. That length, that number is not important. Important point is this part. So now the matrix M will satisfy this condition: 0, 1, 1, 0, M transpose is equal to 0, 1, 1, 0. So it's a little different from that thing, right? I mean, and then if you solve this, I think you should get, I mean, I've never checked it myself, but you should get the solutions are e to the lambda and e to the minus lambda.
So, but in the end, we have two different versions of representing the same thing?
Yeah.
They are belong to the same.
Precisely. This is exactly like what I described for the O2 versus U1. You see, I mean, maybe, yeah, in fact, these questions, both the questions are related to the same issue. Huh? So remember, we discussed O2. In the O2 case, SO2 case, let's say, you had cos theta, minus sine theta, cos theta. This was the way xy was transformed, right? For the Euclidean case, where the length was x squared plus y squared. Okay. But then he went to the coordinate z, complex coordinate z, which was x plus iy. And now you see I have an I here. In terms of z, the length was z bar z. Length square was z bar z. And in this case, the transformation was very simple. Z goes to e to the I theta z. And of course, z bar, then complex conjugate of that, goes to e to the minus I theta z bar. So this is exactly the identical, except that you have to put i's or remove i's and so on and so forth. So this I, if you remove, that is what becomes e to the lambda, right? And this becomes e to the minus lambda. And here also there is no I. You see, here you have just x plus y or x minus y. There is no I. So it's exactly like that. So just like what we said, this language, I mean, going to the complex language, we said that SO2 is the same as U1, right? We said from this discussion, we said that SO2R is the same as U1. Okay. The same way here, by the way, I should put a notation here. The notation for this group is again a 2 by 2 matrix, right? But it's not exactly orthogonal. It satisfied this more complicated condition, which was, I erased it, M transpose eta M was equal to eta, where eta was a Minkowski metric. In this case, the terminology, the language, is that this group is called SO 1,1 R. This 1,1 means that one of the metric component comes with a plus sign, other comes with a minus sign. As opposed to the previous case where we use the notation SO2R. So in this case, both the directions were coming with a positive metric. Okay. Here we are saying that one direction comes with a plus, other direction comes with a minus. Or more generally, let's say in the 4-dimensional case, we'll have SO3,1R, which means three of the directions come with the one sign, and one direction comes with the opposite sign. That is the 4-dimensional Minkowski spacetime. Okay. So that is the group. The dimensionality of this group of these two groups are the same. Okay, because that is just the question of how many parameters are there. You have a certain condition, which defines the matrix, and so how many parameters are there? It will be the same. Just like here, it was one parameter. Here also is one parameter. As we saw, lambda. There's only one lambda, right? One parameter. There's also one parameter. Same way, SO3,1 or SO4, R, which will be Euclidean 4-dimensional space. Okay, they have the same dimension. But the difference will be that the difference you can see here. This is e to the lambda. You see, whereas here it's e to the I theta. Okay, this is compact because theta plus 2 pi is the same, right? So this is just a circle. It's a compact space. Whereas this lambda, e to the lambda can be anything. From 0, minus infinity to plus infinity, anything, right? And it keeps growing, it's unbounded.
When we say that we scale this with e to lambda and this is with e to minus lambda, is there anything special about e? Could we choose any other number like 2 to the lambda? Or
Oh yeah, sure. Yeah, no
minus
problem. Yeah,
lambda?
no problem. Yeah, it is I mean, that's the same. If you say 2 to the lambda is the same as e to the power of log 2 lambda, right? Just call this as nu, some lambda prime. So you can always, if it's a power law, you can always write it as exponential. No?
Yeah, sure.
Yeah. Exponential is more convenient, I mean, because it's a natural number. Exponential has very nice properties. E has a very nice properties. So it is more convenient to use E rather than, but yeah, you can use any power. It's as a power law, basically. Right. So,
but the transformation will not be that arrangement. I mean, you will not have cosine h or sine h. You have some against the.
no, that's just a matter of redefining lambda. You see, call this the lambda prime.
I see.
Right.
So it's
Yeah.
cosine.
It will become cos hyperbolic lambda prime. Or if you rewrite in terms of log original lambda, this will be log 2 times lambda. That's a redefining of lambda. Yeah. So yeah, this is the. So now the question is just like here, we had SO2R and U1 by going from xy coordinates to the complex coordinate, which was a combination x plus iy. We saw that the two groups are the same. You can ask the question, what is the group here? You know, here we have SO1, 1R, but once I went to the light cone coordinates, it was just multiplying by number. But that's just the R plus. That group is the R plus. Let me just call it R plus. Then define what is R plus. You see, in the case of when we have a real line itself, the set of all real numbers, yesterday we said this is the group, but under the addition, not under multiplication. Why? Because the 0 has no inverse. Okay. However, if you take R plus, which means the set of all positive numbers, positive real numbers. Okay. So this is the set of all positive, strictly positive. Not 0 is not a part of that. Strictly positive. All strictly positive numbers, positive real numbers. Okay. Then this forms a group under multiplication, under the usual multiplication. Because for every number, every positive number, inverse is also a positive real number. Right? So this is the group. And this is in fact that group. Because you see what you're doing, e to the lambda is some real positive number, real positive number, right? So you're multiplying by that. Okay. So x is some number. Let's take x plus to be positive. Okay. Yeah, let's take x plus to be positive. Because by the way, this group that I mentioned, I mean this is SO11, R. Here I've already taken the connected component, just like for O2, we had the two disconnected components, and we took SO2R, and that SO2R was related to U1. No, because here also the determinants can have various signs. No, for this case, SO11 also for O11 also you can have different signs. So what I've done by parameterizing in this way, now this is a connected component. If you multiply by -1 here, okay, then it will be a disconnected component from that. So there are various components you can put here. And in particular, if you choose a component which is described by saying that x plus is always positive. So I want to consider only those transformations which leave the length square fixed, as well as not change the sign of x plus. That means this e to the lambda then, x plus is positive, and e to the lambda also is going to be positive. So that would be isomorphic to this group. Yeah, but these are all non-compact groups. The moment you change the signature, it's going from Euclidean to Minkowski, you get non-compact groups. Although the number of parameters will be the same, but they'll be non-compact. There's no bound here. It's not a space. It's not a compact space. You can increase it as much as you wish. Of course, it has many important consequences. I mean, this little change of sign, the metric. I mean, the groups are very different. And as a result, you cannot find unitary representations of these groups, finite dimensional unitary representations of the Lorentz groups. That's it.
It might be a repetition, but to be sure, I need to ask. SO2 was actually identical to the U1 by e to the I theta function, but here we have e to the lambda on the lambda, so this new SO1, is equal to not U1 but R plus.
Yeah, exactly. It's R plus. With this also this condition that I want to impose this condition also.
Can I also say that by looking at parameters, for example, in U1 the phase is a compact parameter, and the U1 group is also a compact group then, but in that case we have no boundaries of R plus, so it's non-compact.
I should also mention that you see, because if you just impose the condition determinant equal to +1 here, which is like what we did for SO2. The determinant equal to +1 will not allow you such multiplications, right? However, you could have changed the signs of all of them. Correct. That will still be determinant +1, but that will not respect this condition. You see, x plus will go to e minus x plus times e to the lambda, right? If you do that, so if you also impose this condition, then you don't allow this minus sign.
So they are not exactly the same.
No. So when I say SO11R, I mean really it's not SO11R, a subgroup of SO11R, right? Which is characterized by also demanding that x plus is always possible. This is what is called proper Lorentz group. This is what is called proper Lorentz group. In a sense, what it is saying, you see, I mean, if you think about this, what is x plus and x minus? You see, we said the one of them is time. No? So let's say x is the time and y is the space. X plus y, so is the light cone direction, right? These are the light cone. So x plus y, x plus increases this way, x minus increases this way. So you are saying that when it's only x plus positive, that is basically saying that I'm going to only look at this part. That's kind of we don't look back here. It's just that you can restrict yourself to that.
It's a one more condition after special.
The determinant condition and x plus these two conditions.
When we say proper, this new condition. When we say proper Lorentz.
This is what is called proper Lorentz group.
I think they classify Lorentz group according to two criterion: whether the first entry is positive or negative, and the determinant.
Yeah, correct.
So this is four
components.
And the discrete symmetries are in the the ones with negative determinant and the negative first entry.
Yeah, correct. This is exactly what it is.
So time reversal and charge conjugation and those symmetries are non-proper Lorentz transforms.
So this subtlety was not there in the Euclidean case. Euclidean case, there's no, I mean, in the Minkowski case, there is a notion of time-like directions or space-like directions, no? Those are invariant under Lorentz group doesn't, if you take a type, because this thing, x square minus y square, okay, this was a length square. This could be positive or negative, no? So for one case, depending on what you call time, one of them is time, other is space. For these two cases, positive, but this length square is positive or negative, you call it either a time-like vector or a space-like vector. So you have these different notions. Those kinds of notions didn't exist in the SO2 case, right? There was no, everything was space. There was no such thing as that. Okay. Now let's see how much time I have. 15 minutes. Maybe I could just, since we start talking about this, to formally define what is a subgroup. Although you already know intuitively from all these examples what is a subgroup, but just to formally define subgroup. So we define. So suppose a group is given to you. A group G is given to you, which means, of course, this group is some set which satisfies all the properties of the group. It comes with the multiplication rule. Okay, so it comes with some multiplication rule. This comes with some multiplication rule. Now, a subgroup, how shall I call it? S? I don't know. I don't know if we use a particular notation for subgroup. By the way, these notes are from one of my colleagues called George Thompson, who gave this course many, many years ago. And I like these lecture notes. I'm just following his lecture notes. And I'm too lazy also to write another lecture notes. So, okay, so there's some subgroup. I don't know what shall I call it. I don't know, G hat or something. Let's say G hat, or H, let's call it H. H is called a subgroup of G if H is a subset of G, and secondly, and H is itself a group, meaning it satisfies all the axioms of the group, properties, definite properties of the group, itself a group, but very importantly, with the same composition rule, not with a different composition rule, with the same composition rule that was in the original G. Okay. You cannot use some other composition rule. For example, I don't know, in the case of say real numbers or something, maybe the original group was defined with addition, right? Or complex plane. Take a two-dimensional. Yeah, take an example. If you take a complex set of complex number, set of one complex number or two real numbers. So you have x and y. This is a group with respect to addition, right? Where I have elements are x, y, and if I have x, y and x prime, y prime, then the composition rule is simply x plus x prime, y plus y prime. Okay, the usual vector addition. So this will be a group under that. The 0, 0 vector will be the identity, and for x, y, the inverse will be minus x minus y. Okay, this is a group. On the other hand, if you consider this circle of unit radius, okay, which was so thinking in terms of complex, if I call x plus iy is z, then e to the I theta, this is certainly a subset of the full complex plane, right? But it's not a group under this. It's not a group under this addition rule, because if I take one vector here and another vector there, the addition of these two vectors will be this, which is certainly not part of this, right? It is a group under multiplication of the two phases, e to the I theta times e to the I theta prime will be e to the I theta plus theta prime. But that's a different composition rule. So this is not a subgroup of the R2. So this is very crucial, that it should be the same composition rule as here. And then you call it a subgroup. All right, and then let me see what else. Because the next chapter, maybe I should do that, because I don't have time to do this. So what now, okay, and I think maybe the rest of the time we can just devote to if you have any questions. But I just briefly mention what will be the future plan. So tomorrow I will discuss the infinitesimal transformations. Okay, because in fact this entire course will be focused on that infinitesimal transformation, because we will see that you can almost understand everything about the structure of the groups, Lie algebras, groups, even groups, and representations. Everything you can understand by studying well the infinitesimal transformations. That's one thing. And we'll also see that process how these infinitesimal transformations are closely related to, I mean, the physics of it. All the conservation laws that we know of, like conservation of angular momentum, conservation of momenta. All of these things are related to some infinitesimal symmetry transformations. Not that they are, exactly. So we will discuss that. Then the next chapter, all this, so tomorrow and I have one more day this week. I will discuss, just like here we discuss the SO2 and U1. Now we'll go to, these groups are very easy, that's why one gives that as a first example. Why is easy? Because they're abelian. They commute. Every two elements commute inside this group, right? So the first non-trivial examples will be SO3 and SU2. That's where you start seeing non-commutativity. And indeed, it will turn out the SO3 is also closely related to SU2. Not exactly like SO2 versus U1, but it's a 2-to-1 map. Okay, those things we'll do. Hopefully, we'll finish that this week. That part will finish. Okay. And the next week will be devoted to SU2 in detail, and the representations of SU2 and so on. So next, several lectures will be for SU2. Okay. Any questions? We still have 5 minutes. Sorry.
Maybe it's an off-topic question. Then, to construct the Poincaré group, we add the translations.
You have to add the translation. Yeah, it's a semi-direct product. I will define semi-direct product later.
Okay.
Yeah,
so
it's
not easy to
no.
We just add which is the
problem with that is the following. I mean, so you can take any of these groups, right? And you can take product of these groups. Those are called direct products of this group. Already, for example, here we said real. I mean, it's this kind of group, right? It's a two-dimensional vector space. I mean, the group is a two-dimensional plane with a multiplication rule being simply the addition of vectors, right? But this is the same. We already discussed before the real line, right? Real line was also a group under addition. Now, what we are doing is we are taking one real line and another real line, right? So this is an example of a product of these two real lines. Okay, but this is a direct product because the addition here doesn't interfere with the addition there. No, but so those are easy. But Poincaré is not the same because you see, if you look at Poincaré is what? So Poincaré is like this, right? I mean, actually, already why is Poincaré? Already in Euclidean space. No? So let's again go to the Euclidean. This are two-dimensional space. So here I have a symmetry, which is a rotational symmetry, right? And also translational symmetry. You can imagine a physical system which has the symmetries, right? Certainly vacuum of the theory should have this symmetry, rotational symmetry and translational symmetry in these two directions. Okay? But so we have a rotational symmetry, which is nothing else but SO2. Okay, let me not even include the parity. Huh? So just SO2 proper. I mean which does not change the orientation. Okay. And you have also R2, which is the R2. I mean, each R is one translation. So I have translations in this and translations in that direction, right? But here, you see, I cannot take it. There's no meaning of a direct product. Why? Because if I make a translation in some direction, let's say here, then I apply SO2 rotation. Then you see this translation itself has changed. So this group interferes with that group. In those cases, you define a semi-direct product. Okay, and basically it's defined like this. Okay, first of all, let's consider the simpler case where not this, but let's say R2 itself, which I can write it as R cross R. Right, the two translations, the previous example I mentioned. Right, in this case, what do you mean by that? This object is a product group. The elements of this group are a pair of elements. So let's call it G1 and H1. So this is an element of that, this is an element of that. Right? And you have to define now, so let's suppose, okay, here suppose infinite dimensional, but imagine it's a finite dimensional group. Sorry, finite number of elements of the group. Suppose there are 10 elements here and 50 elements there, then the product group will have 10 times 50, 500 elements, because this can be any one of the 10, that can be any one of the 50, right? So it's a product. But then I want to define a composition rule in this big group. So suppose I have now G2, H2. I take a G1, H1 element, G1 from here, H1 from there, and another element here, G2 from here, H2 from there. Then the composition rule is simply this: G1 times G2 and H1 times H2, where I should emphasize this composition rule is for this group. Okay, in this particular case, group happened to be the same, right? But in general, I could have a G1 and a G2 group. Right? So this composition rule will be the composition rule of that, and this composition rule will be the rule of that, because otherwise it's not even defined. No? Because G1 and G2 are elements there. Only this composition rule is defined there. So this is the rule of the direct product. Okay, but that I cannot apply for the Poincare. It's like a Poincare group, a mini version of the Poincare group, right? Translation and rotation. That I cannot do because suppose I first do the translation, then I rotate. Okay, that is not the same as first do the rotation and then translate. Okay, so the rotation does. So in that case, what you do, you define what is called a semi-direct product. So you have a, let's say, what shall I call, rotation group. I don't want to use the same symbol R because that's we are using for real numbers. So this rotation group and the translation group. Let's call it translation group. So this is the translation. So the elements of the translational group, I can describe as some vector V. If I'm in 2 dimension, this vector will be 2 dimensional. If it's in the Minkowski space, it will be 4 dimensional vector. And this, okay, in the Minkowski case, of course, rotation will be Lorentz group. Right? It doesn't matter, whatever the rotation is. Either Lorentz group if it's Minkowski, if it's Lorentz signature, or if it's Euclidean, it will be just ordinary rotation. So some kind of rotation. Now, so if I try to take the product of this, I will have a rotation element, G, this belongs to that, and I mean this guy belongs to that, and some translation element here, which will belong to that. Okay. A product group, if I want to define. Now I want to define a product here. So this is G1, B1, with G2, B2. Okay. So the way you define is precisely because, you see, here I have first done the translation and then I'm rotating. But then this guy will get rotated, right? So you see what happens. Let's you take a simple case. Let's take G1, 0. This is one particular element, no translation here. And here, no translation, so identity. No rotation, this identity. And some V2. Okay. Now let's say this acts on some vector. This acts on some vector, let's say X. X is again a vector in this space. So the first guy, what it will do, the first is just translates it. So this will, the first guy, this guy, will translate it to, I still have G1, this guy I still have to do. But the first one takes this to X plus V2, right? It will just translate X to X plus V2. Now I rotate this whole vector by this. So what you're going to get is G1 acting on X1, rotate by rotation, plus G1 acting on V2, rotation. So this rotation group does act on the translation group. So there is no meaning of direct product in the like in the previous thing we defined. In the previous case there was no G was not acting on H. This was a direct product. But here, the way we are defining the transformations, this G1 is acting on the V2. So the proper definition is this product is G1 times G2. This part is fine. Okay, the rotation is rotation. But here it will be V1 plus G1 V2. This is the product. So more abstractly said, it just is that I have two groups, say G1 and G2, but G1 acts on G2 by some automorphism. Okay, there is some action of G1 on G2, which is automorphic. Automorphism in the sense that it preserves the group structure of this group. Okay, meaning an element here maps this group to itself in a non-trivial way, not identity, I mean in a non-trivial way, in such a way that the group operation is preserved. Okay? So if that automorphism is there, which is like here, in that case the composition rule is, but not vice versa, only one way. Only this acts as an automorphism there, but not that group here. In that case, you define the semi-direct product as the usual product for the first element, G1 times first entry, G1 times G2. But the second one, you define it as this guy plus. Plus is because the operation, the composition rule for the translation was plus. No? Otherwise, whatever the composition rule for this second group is, right? So it will be, in general, it will be some or tilde, let's say, whatever the composition rule of the second group is. But the important point is that it has done, this guy has acted as an automorphism on that. So it's more general, it will be like G1 acting on V2, which will be some element of the second group. And then you take the composition. This is semi-direct product. So it's more complicated than the direct product, but unfortunately it appears all over the place in physics, particularly point correct group.
And also in the algebraic sense, semi-direct product, to define semi-direct product, we need to have an action between the groups.
Yeah.
But here in the action in the algebraic sense.
Algebraic meaning it will just take, there is some particular rule which takes an element of
We can consider it as a homomorphism from the first group to the automorphism group of the second group.
So the first group is
what I say is
yeah.
we can consider the action of group G on a group H is a homomorphism from the group G to the automorphism of the group H. So that's the meaning of action.
Exactly. The automorphism group is of course much bigger in general, but this is a particular. Yes. Okay, so then we meet tomorrow. This I always stop.